No questions? Okay, so yes, there were a couple of questions, right, last time. X plus y root 2. Is this a field?
Not the whole.
Yeah, we should do it. Anyway, I don't want to do it now. Okay. Let's start with our topic for today. Is linear codes. So after all, our entire exercise of defining vector spaces and fields was so that we could have some linearity in the encoding process. Right? We don't want it to be an arbitrary code. We want to impose some structure so that encoding becomes easy and hopefully even decoding becomes easy. Now, of course, we should make sure that imposing this structure does not negatively affect us, because after all, you're restricting the class of codes that you can consider. So let's see, what is a linear code? A linear code is simply a vector space over the finite field. So basically, linear code is vector subspace of f to the n over f. You have some finite field which is basically your alphabet. So henceforth we will assume that the input alphabet is always a finite field. And so a linear code is any vector subspace of f to the n. Okay, it doesn't necessarily have to be the whole f to the n, it could be some subspace. And so we'll use the following parameters. So earlier we had an nm linear code. I used these circular brackets or parentheses. So whenever I'm talking about linear codes, I'll use square brackets. Okay, so an nkd linear code is basically a linear code of block length n. So every code word has n coordinates. Since a linear code is a vector subspace, k will be the dimension of the subspace. This is the dimension. This is the length or the block length. And this is the minimum distance. So these are three parameters that we will be interested in. So for a linear code, what is the rate equal to? Sorry? K bar. What is K bar? Okay, so suppose we have a linear code over f2. Okay. So what will the rate be equal to? So in general, for any code, what is the rate equal to? How do we define the rate? Yes. Okay, so in general, for a general code, what is it equal to? For an nm code, n is the block length, m is the number of code words. Correct. So it is log m to base 2 divided by n. So log of the number of code words or log of the number of log of the message size divided by n. Right? Okay, so now for a linear code, what is m equal to? So a linear code is a vector subspace over F, and K is the dimension of the linear code. So how many possible code words can there be for a general field? Size of F power K. Size of F to the K divided by N is K log size of F divided by. So this is the number of information bits that you are transmitting per channel use. Okay, so let's take an example. Okay, so even before that, now you know that a linear code is a vector subspace over F. What are the different ways in which you can specify a linear code or a vector space? What do you need in order to describe a vector space or a vector subspace of Fn? Yeah. Okay, the alphabet that's always there, but I'm giving you the space, right? So this is the underlying vector space, and I'm considering a dimension k subspace of this vector space, correct? So if I asked you to pick one subspace, how would you describe that subspace to me? Okay, so would you specify all the vectors in that subspace? A basis, right? So if you specify a basis for the subspace, then that is enough to describe the entire subspace, right? And that is the minimum amount of information that you need to give me, right? Because if you don't tell me what the basis is, there's no way I can generate the subspace. So one way of specifying a linear code basically you tell me what the basis is. And you can write the basis in terms of a matrix. So for now I'll use the following notation that code words are row vectors. Okay? So my vectors are going to be row vectors. I'm just following the notation that is followed in many books. But again, you can always think of them as column vectors if you wish. But this will sort of fix some of the dimensions. Okay, so every code word is basically an n cross 1 vector, correct? Okay, so I can describe the basis in terms of a k by n matrix. Sorry? Oh, sorry, 1 cross n. So it's a 1 cross n vector. So I can specify the entire basis. So I know that the code is of dimension k. So I can specify the basis in terms of the n basis vectors or as a k by n matrix. And this is what I'll call the generator matrix. Okay. So any k by n matrix consists of the basis vectors, with the rows being the basis vectors of that particular subspace. That will be called the generator matrix of the linear code. So is the generator matrix unique for a linear code? Yes, no? Why? The basis is not unique, therefore the generator matrix cannot be unique. Let's take an example. Let me take a linear code which is specified by the following generator matrix. Okay. So can you give me a list of all possible code words for this code? So this is over F2. So the two basis vectors are 101 and 110. Okay. Okay, so one by one. So 101 you said is there. Then 110. Then 011. How did you get that? Is this? What two zeros? Okay, if I multiply with 0, what do I get? How do you get 0 plus? Correct. If you multiply anything with 0, what do you get? So then do you get this particular vector? So you're right about this being a code word, but what are the coefficients of the basis vectors which give you this particular vector? 1 and 1. So this vector plus this vector gives you this particular. Okay, and then any more? Any more? Only 3? Zero, zero, zero. Any more? So what is the dimension of this code? 2. So what is the maximum? What is the number of code words that will be there in this code? But how many code words are there in the code book? 4. So 2 to the 4, 2 to the 2. Size of f to the k is the number of code words or the size of the code book. In this case, it is 2 to the power 2. So that is, and you have 4 code words over here. So the dimension is k. In this case, what is the dimension? 2. So what is the size of the code book? 2 to the power k, or size of f to the power k. In this case, it is 2 to the power k, which is 2 square. Okay. So as we can see, one way of generating a code word is by multiplying the generator matrix with a vector. So you can write each of these as some message vector m1 m2 times 101 110. Right? So if I take m1 m2 to be 0 0 0 1 1 0 and 1 1, I run through the entire code book. So the all zeros message gives me the all zeros code word. Multiplying with 0 1 gives me 1 1 0. With 1 0 gives me 1 0 1, and with 1 1 gives me 0. So this is the code word. This is what we will call the message vector. Therefore, encoding essentially corresponds to multiplying the message vector with the generator matrix. So m vector m times matrix G gives me the code word. Okay. All right. So we looked at seen two parameters in some details, n and k, and how to encode. Now we're interested in how many errors this particular given code can correct. Now in this particular case, let's take G equal to 101110. In this case, how many? So what is the minimum distance of this particular code? Here you have a list of all code words. The minimum distance is 2. Does everyone agree? Okay. So one way to find the minimum distance is, of course, to take every pair of code words and then find the distance between the two. Now for linear codes, it's possible to do it in a slightly simpler way. And that is, instead of finding the minimum distance, you instead find the minimum weight. So in this particular example, we saw that the minimum Hamming distance is equal to 2. But what is the minimum Hamming weight of the non-zero code words? 2. Does this happen for all linear codes? Okay, what if it is not F2? So by definition, this is the the minimum Hamming distance. So it's a minimum among all unequal code words of the Hamming distance between the two code words. So similarly, we can define the Hamming weight code as the minimum over all possible code words C, which is not equal to 0. The Hamming weight for non-zero code words. So my claim, so this is basically the number of non-zero elements in that particular claim, is that for any linear code, minimum distance. Any thoughts? Remember, it's for a linear code, correct? So suppose that the minimum distance of the code is equal to some number d. Okay. So what does this mean? It means that there are some two code words for which Hamming distance is equal to d. Correct? Okay. So now what about C? What can you say about, say, C1 minus C2? So for any general field, C1 minus C2 makes sense, right? Field of C1. Correct. So the Hamming distance between any two sequences is equal to the Hamming weight of the difference between the two sequences. Because in those coordinates where the two are the same, you get a 0 when you subtract. If the two are not the same, then you get some non-zero element. So the Hamming weight of C1 minus C2 is equal to D, but C1 minus C2 is also good because it is a linear code. Correct? So what can you say about the Hamming weight of C? Yeah. C is the code. Sorry? How do you say that it is greater than or equal to? It is the minimum Hamming weight. And I'm telling you that there exists at least one code word whose Hamming weight is equal to D. So can you say that the minimum Hamming weight is greater than or equal to D? No, 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 no. So C is the code book. No, no, no. So C is the code book. Right? C is the code. C1 minus C2 is a code word. There is one code word in this code book whose weight is equal to D. So what can you say about the minimum Hamming weight of the code book? Equal to D? Why? Where? Huh. Correct. But then it does not mean that there is no other code word with smaller Hamming weight, right? I've shown that there exists one code word with Hamming weight equal to D. All I can say is that the Hamming weight of the code is less than or equal to D. At this point, that is all that I can conclude. Now I want to show that it is not just less than or equal to D, it is exactly equal to D. So yep. From which point? Okay. So since the minimum distance is this, you can find two code words whose Hamming distance is equal to D. This part is fine. Okay. Now, do you agree that the weight of C1 minus C2 equal to D? Sorry? Correct. Yes. The Hamming weight is equal to the Hamming weight is equal to the Hamming distance between C1 and C2. So this is equal to, okay. So do you agree that C1 minus C2 is a valid code word? That's all that I'm using at this point. So C1 minus C2 is some code word and whose Hamming weight is equal to D. So the minimum weight, the minimum Hamming weight of the code is less than or equal to D. Because there is at least one code word whose Hamming weight is equal to D. There could be some non-zero code word whose Hamming weight is less than or equal to D, but we are not sure yet. Okay. So what would happen if the Hamming weight of the code is strictly less than D? Can this happen? Why? Which are those two code words? I'm saying that the Hamming weight is less than D, right? Why? So minimum distance is between two code words. You have to produce two code words, right? For Hamming weight, there's only one code. So with this,
that is also part of leading.
Correct. So what all I can say is that there exists some code word. Let's call it C in the code book, such that the Hamming weight of C is equal to whatever this quantity. Call this C prime. Correct. So now can you produce two code words of the linear code for which the Hamming distance is d prime? Which two code? Correct. Okay, so how do you know that you can always code words? Okay, can you give me a more explicit pair of code words? Very simple. So if I give you a linear code, then you always there is always going to be one code word which is part of every linear code. So then what is the Hamming distance between C and the 0 code word? B code word. So the Hamming distance between the code word and the all zeros code word is equal to. Yep. So the 0 vector is going to be a valid code word for every linear code. Directly from there only, like. Which, what do you mean? From there. So, zero. Right? Correct. That point. From where? To prove what? This part? Wait. Okay. I mean, wait. Correct. Yeah, the same thing. Directly from there. That is what you're doing here. We're just expanding it out. I'm just saying. Lastly. Oh, with only this? Only that. But how do you know that there are actually two parts, right? One, you have to show that the Hamming weight. There are different ways to do it, of course, but just this is not enough, because there could be two non-zero code words whose difference could be is smaller than the Hamming weight. For a linear code, you have to show that that cannot happen. For a non-linear code, this is not true. So in particular, for a non-linear code, you can have either of these cases. So the minimum distance could be larger than the minimum Hamming weight, or it could be strictly smaller than the minimum Hamming. Okay. So that's a simple way of finding the minimum Hamming distance. It's somewhat simpler, because now I don't need to look at all pairs of code words. All I need to do is just look at all possible code words, find a code word with minimum Hamming weight, and that is going to be my minimum Hamming distance. The question is, can I do even better? Is it possible to find it in a simpler way? We'll see how that can be done. But before that, so we saw one way of specifying a linear code, which was using the generator matrix. Right? Now, if I give you a vector, so describe a vector space. One way to do it is to specify the basis, right? Or in general, you take any matrix A, right? There is one fundamental or two of the fundamental subspaces associated with the matrix A are the row space and the column space. That is the vector space generated by the rows or the vector space generated by the columns. So if you look at the generator matrix, so a linear code is basically the row space corresponding to the generator matrix. So the code C, one way to write a code is write it as the row space of a generator matrix. So linear algebraically, this is exactly what we have. But now, corresponding to any given matrix A, there are two other fundamental subspaces associated with this. Which are they? Yeah. So given a matrix A, there are two of the fundamental subspaces associated with this are the row space and the column space. There are two more fundamental subspaces associated with any matrix. Sorry? Correct. So the right null space and the left null space. Right? So the four fundamental subspaces are the row space, the column space, the right null space, and the left null space. And conversely, any vector space, I give you, I specify any vector space to you, I can always write it as the row space of some matrix. I can write it as the column space of some other matrix. I can write it as the right null space of some other matrix, and or the left null space of some other matrix. Do you agree? So similarly, yeah, yes, rows. Right? That, yeah. So it's m times g. Yes. The row space. I'm representing code words as row vectors. If I follow this convention, then it is basically the row space of G. So G is always going to be a k by n matrix, and I'll assume that it is full rank. Now I can also write C as the null space, the right null space of some other matrix H. And this matrix H is going to be called a parity check matrix. So if H is a parity check matrix for code C, and C is any code word, then what can you say about H times C? This is zero vector, or H C transpose should be equal to zero vector. What should the dimensions of H be for an nk linear code? How many rows, how many? Yeah. Huh? So it should be n minus k cross n. And how did you get this? Okay, but what fundamental result did you use to come to this? Okay, but purely from a linear algebraic point of view, yeah, just this. So basically, what is C equal to? This is equal to the null space of H, right? Or in other words, it is the set of all vectors C in f to the n such that H times transpose is equal to 0 vector. Using this, I want you to show that this should be an n minus k cross n matrix. Assuming that H is full rank. Linearly independent vector. So if I give you a particular matrix, uh, is there some relationship between the dimension of the null space and the rank of the matrix? N minus rank is also what is does this result have a name? This is the rank nullity theorem. So for any matrix H, what exactly does it say? Rank of H plus dt. What is it equal to? What dimension? What is n in terms of H? I'll give you a matrix H. H is maybe a 50 by 100 matrix. What is n? Is n 50 or n 100? So it's a number of columns. So the rank plus the nullity, that is the row rank, plus the dimension of the right null space is equal to the number of columns. So you know that the rank is basically the, assuming that this H is full rank, the number of rows of H plus the nullity should be k, because we're assuming that the code has dimension k, should be equal to n. So the number of rows of H should be equal to n minus k. Okay? Because the null, what is the right null space of H equal to? It is equal to the code by definition. But what is the code? The code is a vector space of dimension k. So the nullity of H should be equal to k. Right? Okay. So, so now there are two, as I said, there are two different ways of specifying a code. If I take a given matrix, some matrix, then if I take the linear combination of the rows of matrix, then I get a code. If I take the right null space of this particular matrix, then I get some other code. Right? I start with a code G. I start with a generator of a matrix G, which is maybe k by n. So if I define the code to be the row space of G, then the right null space of G is also a valid code. Some other code, but it's a code, right? So it's another linear code. So the right null space of G is also valid linear code. And this is what is called the dual code of C. Right? So what can you say about the code words of this particular code and the code words of this particular code? There's some relationship between the two. Some geometric relationship between. They're all going to be orthogonal to each other. So if I take the inner product between a code word and any code word in the dual code, then that is always equal to 0. So let's take an example. Go back to that code that we had 0 1 0, and we saw that. So let us take this to be G. C. So C is consists of the following code words: 0 0 0 0 1 1 1 0 0 1 1. So this is the entire code book. So for this code, can you give me a parity check matrix? What will be the dimension of the parity check matrix? How many rows, how many columns? We have 1 cross 3 matrix. So all can be all zeros. Correct, but will the right null space of that matrix give you this particular code? So do you agree that this is a parity check matrix for this particular code? Remember, there are two things to check. One is that h times any code word, or h times c transpose for any code word c, is equal to the zero vector. Also, you should also check that no other sequence gives you, or no other sequence which is not a code word gives you h times c transpose equal to 0. So you must ensure that h times transpose equal to 0 if x is a valid. Yeah, x transpose, yes, yes. But you also have to ensure that it happens only if so. Let us maybe take another example. Right now, I'm just guessing, right? At this point, we're just guessing. There is a more systematic way to get it, but right now, we're just guessing. Any sequence other than a valid code word is not going to give you. In particular, if but as long as the dimensions are satisfied, you should be fine. So if H is a full rank n minus k by n matrix, such that H x equal to 0 for all code words, then that is sufficient. Right? Because the right null space has dimension equal to k. Okay. Okay. So in this, let us maybe take another example. So let us take this to be a generator. Okay. Let me take H to be this matrix. Or in other words, I could take H to be G. Now, this is a matrix H. I take another matrix H prime, which is 1 0 1 1. Okay. These are three matrices. Now this generates a code C, right? Basically the row space of this matrix. Can you list all the possible code words? Zero? Correct? Okay. Now, let's look at H prime. Okay. What can you say about H prime? Does H prime have full rank? What is the rank of a matrix? What is the rank of H prime? Correct. What is the rank of this? Two. So it is not so a matrix is full rank only if the rank is equal to the minimum of number of rows, number of columns. So for a fat matrix is full rank only if the rank is equal to the number of rows. Okay. In this case, so this matrix is not full rank. But now, what about H prime times any code word? What does it give you? Zero for every code word. Right? I'll take one more matrix, double prime, is the following matrix: 1 0 0 1 1 1. Take a trivial example. This is not a full rank matrix because the two rows are the same. What can you say about H double prime times any code word? So now I've given you three different matrices. They are of different dimensions, different ranks. Which of these are parity check matrices for this particular code? Okay, Hg transpose have to be 0. Fine. So in the first case, is Hg transpose equal to 0? What about the second one? In all three cases, H times D transpose. So if you conclude that all these three are valid parity check matrices, okay, number of rows, fine. You're saying number of rows. So you're saying that this is a parity check matrix for the code. You're saying the second one is not, and the third one you're saying is. I want yes or no answer. Yes or no. Okay. Third one you're saying yes. Again, what does can be mean? Yes or no? What else will you check? Okay, how many of you say that H double prime is a parity check matrix? Yes. How many say yes? Okay, how many say no? It is not a parity check. Okay, why? You don't get? What is the definition of the on the row space, right? So this code is kind of special. I mean, so happened that this was, but okay, okay. So what if it is not full rank? So let us go back. What is the definition of a parity check matrix? So any matrix for which the code is the right null space of that particular matrix is a valid parity check matrix. So now let us revisit our example. There are three matrices. The right null space of this particular matrix, what is it going to be? So what are the dimensions of the right null space of this matrix? Use the rank nullity. Why? Okay. How many columns are there? So two, right? Okay. So that is fine. So now can you list the entire right null space of this matrix H? So there are four sequences in the right null space, right? So is the right null space equal to C? No? So you know that the number of vectors in the right null space is what? No, you said that the dimension of the right null space is equal to 2. So now what is the number of vectors in the right null space? Correct. How many vectors are there? I know, but how many total number of vectors are there in the right? If I give you a vector space of dimension k over f2, then how many vectors are there in that space? 2 power k. Right? So in this case, how many vectors are there in the right null space? 4. So, and is every code word there in the right null space of H? Yes. So can there be any other vector in the right null space of H? Oops. Yeah, that's it, right? So you can't have any more code words. So the right null space is equal to C, correct? Okay. So now let's look at H prime. Okay. What is the dimension of the right null space of H prime? Rank is 2. Yeah, but the rank of the matrix is what? 2, right? H prime. So the nullity is 2, right? Is every code word in the right null space of H prime? So what is the right null space of H prime equal to? Is it equal to C? You should learn. How many vectors are there in the right null space of H? What is the size of the right? 4 vectors. Everyone agrees? You agree? Okay. Do you agree? Okay, what is the dimension of the right null? Do you agree with that point? Dimension of the right null space is equal to 2. What is the rank of H? Number of columns is 4. So using the rank nullity theorem, the nullity is equal to 2. So the dimension of the right null space is equal to, that is fine. At that point it is okay. So how many vectors are there going to be in the right null space? 4. So you need to find 4 vectors which are in the right null space of H. So let's forget about what we have over here and try to compute the right null space explicitly. 1, 0, 0, and 1, 1, 1. Basically, what I need to do is solve the following system of linear equations. Is equal to the all zeros. Fine. Okay. So let us start with some guesses. I know that there are only 4 vectors. So if I can somehow produce 4 vectors by this, I'm done. I have computed the right null space. So since this should be all zeros, the all zeros vector will obviously be the first guess. First guess would be zeros. So 1 is done. Now I need to find another vector which satisfies. Can you guess something? 1001 satisfies this system. 1001 into 1001 gives me 0. 1001 into 0110. 1001 into 1111 also. Fine. Second vector in the right null space of this H prime. Any more guesses? 110. All ones. So I have 4 vectors, and this is all of the right null space. There are no more vectors in the right. But what about this? This is equal to C, equal to the code book over there. So really, the right null space of prime is equal to C. So it is a valid. Now let us look at the last matrix. 1001, 1001. Okay. You want to know whether this is a valid parity check code or not. Now H prime times any other code word gives me the all zeros vector. But I want to know whether the right null space of H double prime is equal to the code or not. Now H double prime, what is the dimension of the right null space of H double prime? So the right space of H double prime, this has dimension 3, so it is going to contain the code, but contains other vectors as well, beyond valid code. So this is not valid parity. H double prime is not a valid parity. That is why the rank really matters. To be careful, just because the size of the matrix satisfies all the constraints. You also have to ensure that A, the size matters, but what is more important is that the rank. So both these are valid parity check matrices, but they have different dimensions, they have different sizes. But the ranks of these two are the same, they're both equal to 2. Now, so this was one example. The best thing is to work out little examples of. But this particular code, by coincidentally, this code is kind of special because this is the code. Now you can try to compute the dual code. It's basically the set of all vectors which are generated by the parity check matrix. Now that also turns out to be equal, but in general that is not true. So this is an example of what is called a self-dual code. This is kind of a special example of self-dual code. Now, a simple way of checking whether a code is a parity check matrix or not is the following. H is a parity check matrix for any, see if the following holds. So G or H times G transpose is the zero matrix. What are the dimensions of this? So, whatever, n minus k cross k, or in general that doesn't have to be the case. If this holds and the rank of H is equal to n minus k or equal to n minus rank of G, where is any generator matrix. Okay. Now, this is an easy way of computing the parity check matrix. So one way is, of course, we did kind of a cumbersome process where we checked whether something was a parity. You can compute the null space and so on. But there's a slightly easier way. So given any G, you can always bring it to the row reduced echelon form. Echelon form, and you bring it to the following form. It's identity matrix, and then there's some other submatrix. So this is k by k. This is an k k by n, k rows and n minus k. Right? Now you can check that one way of constructing the parity check matrix. It's not the only way, but one parity check matrix is always going to be of the form A transpose identity A n minus k. And it's easy to check that this is a parity check matrix. You just look at H times G transpose. What is this going to be equal to? It is going to be equal to A transpose I But what is G transpose equal to? The transpose of this matrix. So it is I A transpose. Just multiply these submatrices, you get A transpose plus transpose, which if it is a binary field, then it's equal to 0. But if it is not binary, you just have to take minus A transpose is 0. Okay, that's one part we haven't completed yet. To ensure that this is a parity check matrix, you have to ensure that the rank is correct. So what is the rank of this particular H? It's equal to n minus k, because kind of almost in the row reduced echelon form, but with the columns integer. Correct? You have an identity submatrix sitting over here. So the rank is equal to H, because there are you can find n minus k linearly independent columns. So rank of H is equal to n minus k. So the rank is equal to n minus k, and H times G transpose is equal to 0. Therefore, this is a valid parity check. What do you mean add every code word? Okay. Again, this is difference between a generator and parity check matrix. So, okay, just homework, and then we'll stop. Take the following. Okay, yeah. So for this, suppose that this is the parity check matrix. Okay. So find the code corresponding to this parity check matrix, and also see if what you're saying is true or not for this particular parity check. We'll maybe stop here because the next class is about to start.